Why parametric BOM is becoming the backbone of digital manufacturing. For decades, engineers and designers have trusted a fragile assumption that a drawing, once completed, could be reliably translated into materials, cost, and production steps. In practice, this assumption rarely holds. Between a parametric model and a finished product lies a critical layer where most errors, delays, and hidden costs are born: the bill of materials. Traditionally, BOMs are assembled manually, updated separately from geometry, and validated only after design decisions have already been made. But what if the BOM were not a document created after design? What if it were a direct computational consequence of the design logic itself? This is the paradigm introduced by BeeGraphy's parametric BOM workflow. The core problem with traditional BOM workflows. In conventional CAD/CAM pipelines, geometry is modeled first. BOMs are extracted later. Cost estimation is handled separately. Any design change requires rechecking all downstream data. This separation leads to inconsistencies between drawings and material lists, delayed cost feedback, manual reconciliation across teams, scalability limits in customized production. In short, geometry and production, truth, drift apart. Why parametric models? Change the nature of BOMs. A parametric model is not a static object. It is a system of rules, dependencies, and constraints. When geometry is defined algorithmically, dimensions are computed, not drawn, quantities are derived, not assumed, relationships are explicit, not implicit. This makes the model inherently capable of producing accurate, up-to-date material data, if the system is designed to expose it. BeeGraphy treats BOM generation as a native function of parametric logic, not as an external export step. How BOM generation works in BeeGraphy. Step 1. Define the parametric logic. The product is described through parameters: sizes, counts, spacing rules, repetitions, materials, tolerances. Step 2. Extract measurable attributes. From the parametric graph, BeeGraphy computes lengths, areas, volumes, quantities of repeating elements, segmentation, and modular breakdowns. Step 3. Translate geometry into material consumption. Geometric metrics are mapped to real materials: surface area, sheet material usage, linear geometry, profiles, beams or tubes, volumes, mass and weight, repetition, fasteners and connectors. Waste factors, offsets, and allowances can be embedded directly into the logic. Step 4. Output: a structured BOM. The result is not a screenshot or a static table, but structured data: component names, material types, dimensions, quantities, finishes, calculated totals. This BOM remains linked to the parametric model. Why this matters for configurators and custom products. When a parametric model is connected to an online configurator, each user interaction changes parameters. Geometry updates instantly. BOM updates instantly. Pricing logic can respond in real time. This enables live cost feedback, error-free customization, automated production preparation. The BOM becomes a real-time interface between design intent and manufacturing reality. From BOM to pricing and production. Because the BOM is computed, it can directly feed automated pricing rules, supplier cost databases, production scheduling, CNC, CAM preparation, ERP, or CRM systems. This collapses what was once a linear, error-prone chain into a single computational flow: parametric logic, geometry, BOM, price, fabrication. Educational and industrial implications. For universities, this approach shifts education from drawing objects to modeling systems, from visual correctness to production correctness. For manufacturers, it enables scalable mass customization, reduced pre-production labor, predictable costs, faster order-to-machine cycles. In both cases, the BOM is no longer an administrative artifact. It becomes a source of truth. Conclusion: BOM as a computational outcome. In BeeGraphy, the bill of materials is not an afterthought. It is the inevitable result of well-defined parametric logic. When geometry, materials, quantities, and costs all emerge from the same computational model, design and production stop arguing. They agree by construction. This is not just an efficiency gain. It is a structural shift in how products are conceived, validated, and manufactured. A call to educators, engineers, and manufacturers. If your workflow still relies on manually updated BOM spreadsheets, delayed cost validation, design decisions disconnected from production data, then the question is no longer whether this will change, but when. We invite educators, researchers, and industrial teams to explore parametric BOMs as part of the design logic itself, and to rethink where design truly ends. In a computational world, a product is not finished when it looks right. It is finished when it computes correctly.